In this problem, we're applying the divergence test to a series, and the question says, show that the series passes the divergence test. What I mean by that is when we run it through the divergence test, we are not going to prove that it diverges. That gives us some hope that it converges, but it doesn't prove that it converges. Then we're going to come up with a way to test for convergence in part B, and we discover the thing actually does diverge. So the divergence test is just to check that the size of the terms in the sum is at least going to 0. That's kind of just the minimum requirement if you want something to converge, but it doesn't guarantee it. So what I'm going to do is take the limit as n goes to infinity of my nth term, n over 1 plus n squared. And I could handle this sort of semi-formally and divide the top and bottom by the highest power of n that appears in the rational expression. So I have 1 over n in the top, and then a 1 over n squared, and then a 1. And we're going to say the limit of 1 over n unambiguously goes to 0. The limit of 1 over n squared goes to 0. So I end up with a 0 over 1, which evaluates to 0. So at least the terms that I'm adding into this series are getting close to 0 as n gets large. But again, that doesn't guarantee that the thing is going to converge. You have to have these going to 0 fast enough to still add up to a finite sum. So how are we going to test for convergence or divergence? We simply use the integral test on this. So I'm going to compute the integral from 1 to infinity of the related function x over 1 plus x squared dx. And you might notice this thing is set up so that the numerator almost has the derivative of the denominator in it. So I'm just sort of constructing the chain rule backwards here. I need a 2 in the numerator in order to get the derivative of the denominator up there. So I'm going to put a 2 in there and compensate for it out in front with a 1/2. So I have a 1/2 natural log of 1 plus x squared evaluated from 1 to infinity. And the natural log function never stops increasing. The natural log of infinity is infinity. So I have natural log infinity. And not that it matters at this point, but I'm going to subtract my lower limit, and I get minus the natural log of 2. Natural log of infinity, that blows up to infinity. All right, so my improper integral from 1 to infinity diverges, and that guarantees the series itself is going to diverge. So when I add up all these terms, even though they're getting arbitrarily close to 0, they're not doing so fast enough to make it so they add up to a finite number.